Um, okay, so let's start with I thought a quick review of what last week was about, and then we'll briefly review what this week is going to be about, and next week, just so you know the basic goalposts. Okay, so last week, was primarily about geometry. Just to briefly review. So the first lecture, you'll recall, we basically tried to briefly sketch the derivation of I guess we started with differential geometry, and in brief said there were basically 3 steps conceptually. There's the step where you just introduce the manifold and tensors over the manifold, and there's rather limited geometry you can do at that point, but by the time you get to step 2, where you introduce a connection or a covariant derivative on the tangent bundle in which these tensors live, then there's a lot more available to you. In particular, there's the notion of curvature and the Riemann curvature. And then finally, you introduce a metric or a notion of distance on your manifold. So now suddenly curves have distances, and there's a new meaning for what a geodesic is. It's a special curve that extremizes the distance, or its distance is invariant under first order under tiny perturbations of the curve. Okay, then we derive sort of the action for GR and Yang-Mills theory in parallel. We said GR, you start by building using the commutator of 2 covariant derivatives to build the Riemann curvature, i.e. the curvature on the tangent bundle. Whereas you use the commutator of 2 gauge covariant derivatives to build the curvature on the gauge bundle, also known as the field strength in Yang-Mills theory. And then from here, well, in this case, because all these indices are of the same sort, we were able to build an action that was purely linear in the curvature, whereas here, we couldn't do that. We had to build something that was quadratic in the curvature. And so in that way, by just that was a short argument about just going for basically the simplest thing. We get the action for general relativity on the one hand, and the kinetic term for Yang-Mills theory on the other hand. And then for the rest of the matter, we drew this table that had the gauge groups along the top, SU3, SU2, and U1, and then we had a list of the non-gauge fields, all the other fields in the standard model, the fermion fields, and the Higgs field down at the bottom. And once we said that you can think of these guys as tensors just like anything you had met previously, except now instead of a tensor index, instead of a tensorial index that lives in the tangent bundle, this guy has a spinor index that says how it transforms under Lorentz transformations. And then in addition, it may carry other charges and indices according to this table. And just like when you're trying to build a scalar action in general relativity, you're trying to make sure you build some object where all of the indices are contracted up invariantly, so there's no hanging indices to transform. So that the object is invariant under the transformations relevant to those indices. Here, we just play the same game. We write down the most general thing we can think of that is invariant that has no hanging indices of any sort, and so is invariant under all the transformations that we want the standard model to be invariant under, and that's how we get the action for the standard model. Okay, and that again was just to kind of recap previous courses, and also just to set the stage that this action, GR plus the standard model, works perfectly in all laboratory tests and everywhere in the solar system. But in some sense, the exciting thing about cosmology is that increasingly as you look harder at the universe beyond the solar system, it seems this model doesn't work. And the question is, what's going on? Is it GR being modified? Is there physics beyond the standard model? What can we learn from cosmology about those things? Okay, lecture 2. We met the most important metrics in physics, the maximally symmetric metrics, the Friedmann-Robertson-Walker metrics, which are the actual metrics that appear to describe our cosmological universe. And again, these are nothing but the metrics that can be sliced into three space directions and a time direction, such that at each moment the spatial direction is one of these maximally symmetric spaces, but then the time evolution can be whatever. We don't know. We don't understand the basic principle. We empirically determine the time evolution here, and we use that to then infer via Einstein's equations what matter is present in the universe. And then finally, there are the black hole metrics, which we didn't really get to see in any detail at all, except to say that they're awesome, and especially the Kerr metric is awesome. Okay, then in lecture 3, lectures 3 and 4, we basically got to know that if you want the FRW metrics from the geometrical standpoint. So the focus was largely on, we didn't say much about what particles were present, or we really didn't say much about, you could have basically never had a course in anything to do with matter in your life, and you still could have understood last week's lectures. But so in particular, let's see, in lecture 3, the kind of main probably takeaway message to remember is that we derived from the geodesic equation that in FRW spacetime that the magnitude of the spatial momentum drops as 1 upon a, the scale factor. So it drops proportional to 1 over a as the universe expands. And now this will be a theme throughout the class. It's just helpful for categorizing things in your mind. This has sort of one meaning for relativistic particles. There's a way that relativistic particles behave and a way that non-relativistic particles behave. And thinking about those two limits is usually, first of all, usually they're simpler than the general case. And secondly, usually they get you all the physics that's actually important for understanding cosmology. And so in the non-relativistic limit, this says your speed relative to co-moving observers, relative to the cosmic rest frame, drops as 1 upon a. And so this is why this is called Hubble drag. This is why you and I are not surprised to be at rest with respect to the cosmic rest frame today, nearly. Whereas for relativistic particles, this says that their frequency drops as 1 over a, or in other words, their wavelength stretches as 1 over a. That's the so-called redshift. We see the spectral lines coming from more distant galaxies. They appear to have been stretched to longer wavelengths in proportion to how far away they are. That's called Hubble's law, and that historically was how the again, I read over the weekend that this actually is supposed to be called Lemaitre's law. Apparently Lemaitre discovered this one too. Lemaitre is he's getting treated unfairly left and right in this course, but he was, yeah, anyway. Okay, and then lecture 4 was about how matter and how in a crude sense, in a geometrical sense, let's say, how matter interacts with the geometry. First of all, as the universe expands, we saw that a component of the universe that has pressure equal to a constant W times its density, if that's its equation of state, because it turns out that in the current model of the universe, it can be very well modeled, apparently perfectly modeled so far, by consisting of basically several different components, each of which has an appropriate value of W. So for such a component, we said that it dilutes as a to the minus 3, 1 plus W, as the universe expands. And so in particular for matter, for relativistic particles, again, if we break into the relativistic and non-relativistic case, for relativistic particles, they have W equals 1/3, a fact that we'll derive more correctly later in this lecture. But they have W equals 1/3, so that means that they redshift is a to the minus 4, whereas non-relativistic particles like elements of the periodic table, or you or me, they have W equals 0. In other words, their pressure is essentially negligible when compared to their energy density, which is dominated by their rest mass energy density, mc squared over volume. These guys dilute a little bit slower. They only dilute as a to the minus 3. And finally, there appears to be a tiny little smidgen of energy density in the universe, which has recently, despite being a smidgen, come to dominate the energy budget in the universe because, according to this equation, it only dilutes as a to the 0. In other words, while everything else dilutes, it does not dilute. It's the so-called vacuum energy. It just hangs around at some constant value. And so it shouldn't be surprising that even though it's ultra tiny, it eventually came to dominate sufficiently late in the universe's history. And yeah, so we ended last week with a sketch of basically the evolution of the universe in the so-called lambda CDM model, the standard model of cosmology, in which first there was a radiation-dominated epoch. So again, we were plotting log of the density versus log of the scale factor. So in other words, as the universe expands, the scale factor and log of the scale factor gets bigger. So initially, the universe was dominated by radiation density. The radiation-dominated era then ended when matter density, which dilutes more slowly, took over. And so then we had a matter-dominated era when this was the dominant component. And then finally, just recently, we appear to have entered the dark energy or vacuum energy-dominated era. We live right after that transition point. In tomorrow's lecture, we will meet, as a first application of what we're going to do today, we'll get to know the cosmic microwave background, which is one of the most important bits of information we have about the early universe. And it dates from right after the radiation-dominated era ended. And then there was also in tomorrow's lecture, we'll meet big nucleosynthesis and show how, with a back-of-the-envelope sketch, you can explain basically the observed fact about the cosmic abundance of the light elements, and thereby convince yourself that this model really is, even though it's the Big Bang model really is correctly describing the physics of the universe, even back at 1 second after the Big Bang. Okay, so that was last week. Yeah, are there any questions about that? Yeah. What did I do? Yes, sorry, thank you very much. Sorry, lambda is proportional to A. Yes, I should say comments or corrections. Okay, so now this week, this week is basically meet the matter. So if last week was all about more or less just how the geometry behaves, what we want to do, well, today we're going to basically meet the essential concepts in thermodynamics or stat-mech in an expanding universe. There are just a bunch of basic formulae and concepts that we're going to need for the rest of the week. So we're going to begin thinking about those today. And then tomorrow, the application will be to the two most famous applications of this. Understanding the cosmic microwave background, which, as I say, is really like the gold mine of information that has been by far the dominant thing that's been useful so far in actually learning about the universe, and Big Bang nucleosynthesis. And then the rest of the week, we again are going to apply these concepts to understand what we do and don't know about dark matter, dark energy, and particle genesis, baryogenesis or leptogenesis. Basically, why all of the stuff in the universe why all the particles and antiparticles in the universe didn't annihilate away to nothing in the early universe before we ever had a chance to come along. So, particle genesis. Okay, yeah. So that includes most of our. Those include three of our most basic current hints for physics beyond the standard model. And then next week, without getting into detail, next week is about basically we're going to realize that, just like we're currently realizing that, we basically only looked at geometry last week. There's actually matter in the universe too, and there's interesting stuff when you begin to bring it into more focus. Next week, we're going to realize we forgot about the basic question of where did it all come from. So what's the sort of what theories are there about the origins, and in particular the initial conditions? We're also going to realize that we have, for the most part, modulo a few points this week where we have been, we'll continue this week to treat the universe as if it's perfectly homogeneous and isotropic. In other words, perfectly uniform on a spatial slice. And of course, if you actually look out in the universe, or in this classroom for that matter, it's not perfectly uniform. There are some places that are more dense than others, and that's really our main mine of information about the universe. It's represented most cleanly in the cosmic microwave background. But yeah, so where did those density perturbations come from? What was their initial spectrum like? What do we and don't we know? That's another of our most basic clues about physics beyond the standard model and how the universe began. So inhomogeneities. Perturbations. Yeah, we'll discuss what, in the process of doing that, we'll also realize that we've been essentially neglecting or not thinking about quantum mechanics throughout the first 2 weeks of the lectures. And so we get into quantum mechanics and quantum field theory in curved space-time, how quantum field theory behaves intrinsically differently in curved space-time, and how that is, well, according to the leading theories, that the behavior of quantum fields in curved space-time is probably at the root of where the primordial inhomogeneities, the initial spectrum of density perturbations, came from. And we want to discuss the sort of connection of all of that to black hole thermodynamics and the Unruh effect. Okay, so any questions or thoughts about that? Is it time? It's probably too early for a joke. Since this lecture is, if you want, kind of technical in nature. Well, what I really mean to say is it's not really any more technical or not technical, but it's more about a bunch of tools that we'll primarily be applying to actual interesting beyond the standard model, interesting phenomena beyond the standard model physics later in the week. Because if you want, there's not too much physics punchline here. It's build up to the various punchlines. I want to try to remember to tell 2 jokes at least, just to keep things. But I'll forget if you don't remind me. So yeah, I mean, maybe if we're halfway through, maybe it's already high time I tell 1 joke. The man gets on the train and he heads over to his chair and he sits down across from a man in a nicely tailored suit with a briefcase. People are putting their heads in their hands. You like the last one, I know. So that's why it's going to be all this guy for the rest of the course. So the man sits down, and the man in the suit opens up his briefcase and he takes out his banana and he says, "Yeah, Mom, I think we're going to be there at about 11:15. Okay? Okay, see you soon. Love you." And he puts it back, closes it up, and the man who just got on the train says, what was that all about? And the man in the suit says, "I know, it's incredible, isn't it? The new banana is totally wireless." Stupid, right? Okay. So, thermodynamics and statistical mechanics in expanding spacetime. So, one of the basic objects in statistical mechanics is, so we have phase space, okay? So phase space, which is parameterized by the spatial coordinates, let's say d3x, and the momentum coordinates, d3p. And one of the most basic objects in statistical mechanics is the distribution function on phase space. So if we have a tiny little infinitesimal volume, or I should say, I don't know why I wrote d3x and d3p. What I really mean are the 3 spatial directions are this way, the 3 momentum directions are this way. And now if we have a tiny little infinitesimal volume in phase space of spatial volume d3x and momentum volume d3p, the distribution function fi sub fi of t and x and p tells me how many particles to expect from a probabilistic standpoint in that volume. In other words, the expected number of particles of species I, so let's say neutrinos with left-handed helicity, the expected number of particles of species I in that little volume at time t, and the volume is located at the center of the volume is located at some position x, and momentum p in phase space is given by the distribution function times the volume in question. Okay, and so if we have this guy, so this guy is the number of particles per spatial volume per momentum volume. So now if we want to know what is the actual number density in physical space of that species of particles, so ni of t and x, we just have to integrate over, if we just want to know what is the number of particles per volume d3x here, but we don't care about the momentum, we just have to integrate over the momentum in that strip. So, there. Or if we want to calculate the energy density in physical space, another thing we'll often want to know, then now, well, if this is the number of particles per unit volume, then the energy per unit volume is just the number of particles at that point in phase space times the energy at that point in phase space. And then again, since we only want, usually in cosmology, we're interested in the energy density per physical volume, not volume in phase space. Again, we want to integrate over the strip in the momentum direction. And finally, if we want to get the pressure, again, we get that from the distribution function. Now, so now we have, instead of multiplying the distribution function times the energy, we multiply it by the momentum, spatial momentum squared divided by 3e, and integrate that. So why that factor? Well, you will derive that factor on a homework later on the next homework by comparing, in the first lecture notes, something I didn't cover in class, but if you had a chance to read the first lecture notes, you'll see there was, when I was sort of deriving general relativity, so we had Einstein's equations where g mu nu times 8 pi g Newton T mu nu, where T mu nu is the stress energy tensor. And there are two important examples of stress energy tensors. One is the one that is just obtained. So T mu nu, when you're deriving this equation from the action, you find that T mu nu is given by taking some appropriate derivatives, variational derivatives, of the Lagrangian with respect to the metric. So there were two examples. one is if the Lagrangian for matter, this is the derivative of the matter Lagrangian. If the Lagrangian for matter is just a bunch of test particles, if you're just summing over all the particles you can think of, times their world line Lagrangian, you vary this guy with respect to g mu nu. You get a certain stress energy tensor, which is just the stress energy tensor of a bunch of particles. And then there's the stress energy tensor for a perfect fluid. And so basically by comparing those two guys and imagining that the particles are locally distributed isotropically, you take the particle expression compared to the perfect fluid expression, you'll see that this is the right thing to integrate. So anyway, okay. So those are the general expressions given any distribution function, but there's a particularly important distribution function that is often the physically relevant one, and that is if we think of the particles in the universe whose number density or energy density we're trying to calculate, if they can be approximated as an ideal gas of particles, an ideal gas of bosons or fermions, then there's a famous distribution function that you've probably encountered in a statistical mechanics class called the Bose-Einstein or Fermi-Dirac distribution function. And so it is, just to remind you, it is given by, so if the species has, if you have a species of mass m, or mass m sub I, let's say, for the ith species, and it has various energy states with energy E, and it's in thermal equilibrium at temperature T and with chemical potential mu sub I, then its distribution function, the expected occupation of that state of energy E is E minus mu sub I over T, and then minus or plus 1. So remember, the minus sign here is for bosons. That's if I put the minus sign here, that's called the Bose-Einstein distribution function. It's for bosons in equilibrium. If I take the plus sign, that's the Fermi-Dirac distribution for fermions in equilibrium. And then you know, for free particles, the number of, so that's the occupation number per energy eigenstate. The number of energy eigenstates per unit volume in phase space, there's 1 per Planck's constant cubed, so 1 per h cubed, or in other words, 1 per 2 pi h bar, as I prefer to write it, because I like h bar, and I don't like h. I don't know why, but I'm with everybody. I like h bar, not h. Somehow it's a universally shared preference that I don't know what the basis is. But anyway, okay, yeah. So this is the actual thing we want to plug in here. This is the number of particles per volume in phase space. Okay, so now you plug that guy in there, and again, I won't go through the algebra, but you'll check on the homework that. So basically, you'll just check these guys on the homework because it's otherwise they'll seem like mysterious formulae. But on the other hand, it doesn't make sense to go through them on the board. It'll just be boring. But so first, basically the first thing I do is change variables from the integration variable from the momentum P to the energy E. I can do that because in practice, the expression for the energy will be, the usual expression for a relativistic particle, that E is equal to the square root of its mass squared plus its momentum squared. So that doesn't depend on the direction of the momentum. This distribution function, therefore, also is not going to depend on the direction of the momentum. So really, that just reduces to an integration over the integrand doesn't depend on the direction. The only thing we're really integrating over is the magnitude of the momentum. So we just use this expression to change variables to an integration over the magnitude of E. Okay, and so we get some expressions, and now again, the key thing is to, instead of working with the general expression, all of the really important physics is obtained by just looking at, again, two limiting cases: the cases where the particles are very relativistic or where they're very non-relativistic. Okay, so let's look at what these expressions become in those two limits. So, and again, this is something that will be, this is all a homework problem to check these results in detail in the notes, but from the notes. But so in the relativistic limit, well, so that's the limit where, so in the limit where the temperature is very large relative to both the mass of the species and relative to its chemical potential. So you can basically ignore the mass and chemical potential, basically just set them to 0. Then this becomes, this integral evaluates to just the temperature cubed. And there's a prefactor, an exact numerical prefactor that you'll calculate. It turns out to be a little bit different for one number for fermions, one number for bosons. The exact number is not the most crucial thing, though. The important thing is it's an order 1 dimensionless number times the temperature cubed. And similarly, this is some order 1 dimensionless number times the temperature to the 4th. And this guy is also some order 1 number times the temperature to the 4th. Now, apart from deriving this order 1 number, these relativistic expressions, you can just get them by dimensional analysis. Okay, so in other words, what's going on here? Well, the number of particles per unit volume. So that's a number divided by a volume. Volume is length cubed, and in units where, you know, I may sometimes forget to say so, but I'm always freely setting, like a good high-energy physicist, I'm always freely setting h bar is equal to c is equal to Boltzmann's constant is equal to 1 when it suits me. And in those units, you know, length, 1 over length is equal to units of energy is equal to units of temperature. And so this has units of 1 over length squared, 1 over length cubed, because it's 1 over volume. And according to this, that's temperature cubed. So that since I've gotten rid of, since the other dimensional constants in the expression that are not being integrated over have been set to 0, t is the only game in town. So all this expression could have turned out to be as whatever it should be by dimensional analysis. Similarly, the energy density. Now, instead of number per unit volume, we're talking about energy per unit volume. And so again, if you just use these relations, that then has to be temperature to the 4th. Okay, so that's really the important thing to remember. That for a relativistic species, each of these three guys are extremely useful things to remember, or just know that you can that the right expression is obtainable by dimensional analysis. Number density, energy density, and pressure goes these 3 powers of T. In particular, just to say a word about the physics here. So the number density going as t to the 3. Oh, in fact, let me not talk about that yet. Okay, so let me not talk about that yet. Instead, let's do. So this was supposed to be the expressions in the relativistic limit, and then there are equally important expressions in the non-relativistic limit. That again, you'll check these on the homework. But if you just take the limit instead, where t is now much less than the mass. So now the number density. Now the key point is that, so the expression becomes a little bit more complicated because now there's multiple energy scales that are relevant, multiple dimensional quantities it can be built from. But the key point is that it has a factor. It has some prefactors that you'll derive, but it has a factor which is exponential of minus the mass of the particle over its temperature. So this is saying, in other words, that according to in thermal equilibrium, as soon as the temperature drops below the mass of the particle, its number density begins to be exponentially suppressed. Thermodynamics wants to eat massive particles when the temperature drops below their mass. Okay, thermodynamics hates. Really, it's like something happened in thermodynamics childhood between it and a massive particle, and now it's just really overreacts when the temperature gets low enough. Okay, so the energy density. Well, this one is quite intuitive, but I mean, so this is Boltzmann suppression, basically, right? This is saying in thermodynamics, you're familiar with the fact that the occupation of a state of energy E at temperature T goes as e to the minus E over T. And so here, the mass is the lowest energy state possible for these particles. And so even for the lowest energy state possible, there's this exponential suppression factor, which is why we're getting an expression like that. Here, the energy density, when you're a non-relativistic particle, is just your number density times your mass. And that's just because, well, your energy density is always your number density times your energy. And in the non-relativistic limit, the mc squared part of your energy dominates over the kinetic energy. So this is just approximately equal to your number density times your energy in the non-relativistic limit when your energy is just dominated by your mass. And then finally, the pressure turns out to go as the number density times I should have written this in the same order. The number density times the temperature. So in other words, instead of number density times mass, we have number density times temperature here. But we're working in the limit where the temperature is tiny relative to the mass. And so this expression confirms what we had said in the last lecture, which is that in the non-relativistic limit, P is negligible relative to rho. So in other words, we've derived this fact that we sort of use again and again in cosmology, that W, the equation of state parameter, which again is just defined as the ratio of P over rho, is approximately 0 in the non-relativistic limit. And similarly, I forgot to mention it over here, but another thing you'll derive, if you just, you'll calculate this expression, you'll calculate this expression, you'll get the order 1 factor here and the order 1 factor here. And you'll notice that for both fermions and bosons, the factor here is exactly 1/3 of the factor here. So we'll derive this fact, again, that we use again and again, that for a relativistic species, the ratio of pressure to energy density is 1/3. Okay, let's see. See, only 2 boards. I'm so economical with board space. Also a slow writer, though. It's actually not my goal. I know it actually could be annoying to you that I'm crowding everything together, in which case you would be annoyed by me joking about crowding everything onto the same board. Am I crowding everything together? What about the general size and legibility? Can you guys read what I'm writing? Okay. Okay. Let's see. I think that okay. Yeah, I think that's all I wanted to say. Those are just basic formulae of statistical mechanics. They are true. These are just basic formulae of statistical mechanics. Period. These are the basic formulae of statistical mechanics for ideal gases of bosons and fermions. So really, we're not even talking about cosmology here. I guess one thing I had meant to mention that I forgot to say was that so again, we quickly specialize to the case where it's of an ideal gas in thermal equilibrium, because for the most part, well, we'll get a lot of mileage out of those simple expressions. They turn out to be very, very good for explaining many cosmological situations we'll need. Now, in practice, there are situations like, for example, in describing the, if you want to calculate how the fluctuations evolve from the beginning of the radiation-dominated era up to the moment when the cosmic microwave background was released, so that you can calculate in detail what fluctuations you expect to see, what spectrum of fluctuations you expect to see in the cosmic microwave background, and then go out and check whether observations confirm or do not confirm that spectrum. For that, you need to do better. You want to actually follow the distribution function really in time and space, and even when it's out of momentum, out of equilibrium. And so, yeah, just to mention that the equation, the equation that describes the evolution of the distribution function, just in ordinary statistical mechanics, but then also in curved spacetime, is the so-called Boltzmann equation. So that, again, we are never going to actually solve the Boltzmann equation in this class, or even write it down for that matter. But anyway, it's important to be aware of it. It's used a lot. Maybe the one thing I'll say about it is that often there's the collision-less Boltzmann equation and the collisional, or in other words, the full Boltzmann equation. So the collision-less Boltzmann equation is very simple, and its meaning is conceptually simple. And we talk about it because it's often a good approximation. It's in the case where the particles that are being described by this distribution function are essentially not bumping into each other. They're just zooming through space along their geodesics. Then they're described by the collisional Boltzmann equation. And basically the idea is just that, well, you may recall that when you have a system that's described by a Hamiltonian, if you have a distribution of particles, each one of which is being described by the same Hamiltonian, so you have a little volume and phase space here, and it's filled with a million little particles, and each of those particles is going to follow some trajectory. And, this diagram is terrible because it exactly looks like it violates what I was about to say. But so you follow each of these particles, and they each, here they are at time t equals 0, and then each of them at some later time have moved. So this whole volume has moved and distorted in some other point in phase space. But since the time evolution is all generated by the same conservative Hamiltonian, there is a theorem called Liouville's theorem that says that this volume is equal to this volume. It gets distorted and sheared, but the volume stays fixed. And so, in particular, the number of particles per unit volume stays fixed. So if there's no collisions going on, every particle is just undergoing time evolution according to the relevant Hamiltonian. And so in terms of the distribution function, that says that if you follow that volume through phase space, that the number of particles per unit volume inside it does not change. So now remember, this guy depends on x and p and t. And so if we just expand this out using the chain rule, this says, well, there's one term from applying the derivative, taking the derivative of t. And then there's another term from taking the derivative of x. So we take the partial derivative with respect to x sub j, and then by the chain rule times the total derivative of x sub j dt. and then we need to take the derivative with respect to p. Okay, yeah. So that's the collisionless Boltzmann equation. And again, often it's quite a good approximation if your particles are behaving quite freely. But the more general thing is the collisional Boltzmann equation, where you have to take into account that particles bump into other particles and how fast they bump in, and how, what state they end up in after colliding with other particles, and how frequently those collisions happen. All depend on the distribution function itself. You end up getting some inhomogeneous term here that depends on the various distribution functions, called the collision term. So really, the full Boltzmann equation is like that. Collisionless Boltzmann equation is when this term can be, to a good approximation, neglected. Okay, that was actually more than I meant to say about the Boltzmann equation. But so let's press on. So the next thing I wanted to talk about was entropy. So we already met the idea. So why am I writing? The universe is expanding. The universe has been expanding since a long time ago, and it continues to expand. So in some sense, it's obviously not in thermal equilibrium. It has not settled down to some stationary, not evolving state like you normally associate with thermal equilibrium. So why are we even considering these thermodynamic expressions? How could they possibly end up being useful for us? And so, we already met the analogy between the universe and a piston when we were talking last week. I was saying that you could think if this is the universe, and then you draw a little co-moving volume on the surface of the balloon with a marker, so that volume expands with the expansion of the universe, and you apply the first law of thermodynamics to this. If you think of this as a piston that's expanding with the expansion of the universe, and apply the first law, that's another way to derive this expression that we had before, that the energy density drops as a to the minus 3 1 plus w. So I would like to just to invoke the piston analogy again. You know that if you have a gas in thermal equilibrium here, if you move the piston too fast, you'll drive so if you rapidly move the piston over here, suddenly the gas will be out of equilibrium. It'll relax back to equilibrium at the new volume, but in the process, it'll generate a lot of entropy because you took it out of thermal equilibrium. But if you very slowly and adiabatically, in the limit that you infinitely slowly move the piston out, you remember from thermodynamics, in those adiabatic processes, no entropy is generated. The system manages to stay virtually in thermal equilibrium at every stage. It's just that the thermal equilibrium parameters, the parameters characterizing that equilibrium, gradually ooze to their new value. And so, how do we know whether a system is in thermal equilibrium? How do we know whether we're doing things slowly enough that the system manages to stay in equilibrium throughout? So the process is adiabatic and no entropy is generated. And well, that's just a matter of comparing two time scales. There's one microscopic time scale for the collisions going on, the collisions necessary to keep equilibrium here. They take place with some time scale. That's the time scale with which, if you displace the system from equilibrium, it relaxes back to equilibrium like e to the minus t over some time scale t naught. And then you just have to compare, is that very short or very long relative to the time scale, poof with which you change the system. If the time scale for equilibration is extremely short relative to the time scale that you took to change the system, then it'll stay in quasi-equilibrium. Well, the same situation happens in cosmology. You have a little bundle of gas inside this fictitious volume that I drew on the balloon, or fluid. If the time scale for this thing to equilibrate, if the various rates of particle interactions needed to maintain or establish equilibrium here are 1 second, and it takes the universe 10 billion years to increase the volume here by 1%, it's intuitively clear that the that the equilibration will happen as if the universe wasn't expanding at all. The universe is expanding so slowly in that case that it's irrelevant for the process of equilibration. So that's saying, you know, at any given time, to determine whether the universe is expanding adiabatically or not, you want to determine what is the relevant, what are the relevant processes, scattering amplitudes, let's say, that are maintaining the thermal equilibrium. There's some rate associated with those. That rate will change in time depending on what the density is and so forth of the various particles involved. On the other hand, there's a rate associated with the expansion of the universe. That rate is h is equal to a dot over a. You know, this has units of 1 over time. This is dA dt over a, so units of 1 over time. So these two guys, the question is just which is bigger here? If h is extremely small, in other words, if this time scale is extremely long, if h is extremely small relative to gamma, that's the adiabatic regime in which the universe is going to expand, or the particle species in question is going to expand quasi-adiabatically. In the other limit, equilibrium is not a good approximation. It'll generate tons of entropy, and you shouldn't be using these formulae. Okay, so now speaking of entropy, you know, in a fluid, in the matter in the cosmos can often be well approximated as a fluid, and in a fluid you just like you think of energy per unit volume, even though really maybe that energy can't quite be localized. Similarly, you think of entropy per unit volume. So the entropy in some region here of the fluid can be written as the entropy density in that region times the volume. And so we can get a useful expression for this entropy density again by applying the first law of thermodynamics. So again, first law of thermodynamics says that the energy inside a piston, the change in it is equal to the amount of heat that you add to the piston, TdS, minus the amount of work done by the piston, minus PdV. So this guy, again, the energy in this region here is the energy density times the volume. This term becomes T times d entropy density times the volume, and then minus PdV. Okay, so if I have, if I just expand out the differential here and get rho dV plus Vd rho, and similarly expand out this guy using the Leibniz rule. If I now collect all of the terms proportional to dV, they have to vanish separately. And since I'm running out of time a little bit, I'll just say, so you get, by that argument, you get that the entropy density of this fluid is given by energy density plus pressure divided by T. And so now a sort of last important formula that we want to get this lecture is, so if you're talking now about a relativistic fluid, like in the early universe when the particles were relativistic, and you plug in our relativistic expressions for rho and p here, remember they were both proportional to t to the fourth. So we have t to the fourth over t, so the entropy density is proportional to t cubed. And now, alternatively, we just said that if the universe is in equilibrium, if the universe is expanding quasi-adiabatically, if we're in the regime where h is very small relative to gamma, which again has for much of the universe been an outstandingly good approximation, then essentially negligible energy is generated. And so, as this volume grows, the entropy inside, as this co-moving volume, as the balloon expands, the entropy inside this fictitious region is constant, but its volume is growing as a to the minus 3, as a to the 3. So in other words, if the entropy in this guy is constant, and that's equal to the entropy density times the volume, then if this guy is going, if this is constant, and if this guy is growing as a to the 3, this guy must be dropping as a to the minus 3. Okay, and so now this is a genuinely important result here. So we've said the entropy density of a relativistic species goes as T cubed. On the other hand, in thermal equilibrium or quasi-equilibrium, it goes as a to the minus 3. So this is telling us how the temperature that characterizes the thermal equilibrium drops with the expansion of the universe. It simply drops or redshifts away as it's another one of these quantities that just decays away with the expansion of the universe as 1 over a. So the universe originally, according to this formula, I mean, this is very simple, but it cannot be overemphasized how important this formula is. That this says as the universe expands, the temperature cools, or looking backwards in time, as the universe gets denser and denser, the temperature goes up and up, and so the characteristic energy of the processes going on goes up and up. So in the very early universe, we expect there to have been particle collisions taking place at extraordinarily high energies, corresponding to the extraordinarily small value of a that we think the early universe originally got to. And again, that's kind of an exciting thing about cosmology, that the energies that get accessed here, the energies that appear to have been relevant in the early universe, look like they were probably way above the energies that can be accessed in accelerators here on Earth. When did I start? Oh, yeah, well, I had one more thing to say, but I'll just say it at the beginning of the next lecture. Anyway, that's it. Any questions about any of that?
Why is that the coefficient by d equal to 0? How does that well?
Say it again?
So you derive that S is rho cross P over T by setting the coefficient by d equal to 0.
Yeah.
Why is it equal to 0?
Well, so basically you're splitting the terms into the extrinsic and extrinsic parts. So v can change because okay. So sorry, I went through there's two things to say, David. One is that I was going to suggest this as part of the homework problem, so I kind of don't want to give away the whole solution. So the assumption in more detail here is that so I'm neglecting all chemical potentials here. So all of the intrinsic quantities are assumed to only depend on T. And then, so you really can group the two sides. You can really group the terms into two terms. There's a coefficient that's proportional to dV, and then there's the rest of the terms are all proportional to dt. And then you have to convince yourself that dV and dt are independent of one another. They will not. They can't be functionally related to one another, and so therefore the identity has to hold separately for both differentials. Okay, so I agree. Well, that's so. Wait, we're changing the order of the logic here. I really I would like to leave this exactly as a thing to think about on the homework. Yeah, can you ask me again after you've had a chance to puzzle over it? Otherwise I feel I'll be blowing my material here. On the this is my trying to make me feel bad. Karen is looking at me like no, he's actually not, but he's what can I say? I'm gonna stick to my guns on this one. Let's ask that question again on Monday.